So last time we were studying Gaussian random. What was your name? Can you spell it? I see. 그거 안 불렀으면은 출석 체크 괜찮은 거니까. 출석부가 내가 좀 옛날 건가 봐요. 예? 불인정. 이름이 뭐라고요? 아 근데 이거 매번 내가 이걸 해주기가 좀 힘들어서 번거로워서. 아. 내가 오늘까지는 인정해주고 그러면 다음부터는 이제 불인정하는 걸로. 여기 이름 있나요? 자기 그게? 여기에 있어요? 내가 찾기가 힘들어서 사진이 본인 사진이 있는지. 그러니까 여기 있냐고요. 그러니까 어디에 있는지. 네? 아 그렇구나. 네. 네. 뭐라고요 이름이? 네. 또 있어요? 네. 자, 그러면 네, 다음부터 불인정. So, yeah, we are studying Gaussian random variable which has this probability density function. Okay, and then yeah, we can normalize the Gaussian random variable into a like a standard Gaussian random variable. But before then, we derived its mean and yeah, the variance as well. Yeah, then yeah, we can think of this standardization, which makes our Gaussian random variable. For example, suppose x has the mean of 3 and sigma as 2 squared. In this case, we transform the random variable x using this transformation, and then let's call it as y, which is a function of random variable of an x. So in this case, this linear kind of transformation, y is still a Gaussian random variable, and its mean and the variance will be 0 and 1 respectively. And its probability density function is shown as follows. And then we specifically call this function as this phi or something, right? So this is called the phi. Okay. Yeah, and then yeah, so this is this part is our density function, and this is actually the probability value. So our Gaussian random variable has this PDF, and then given a particular x value, this function will give the area under this curve up to a particular x value. And if x is greater than 0, then as we can see, it's symmetric about 0. So the probability will be greater than 0.5, right? So yeah, we will have some tables for this function phi. I mean the function value of this, this representation, and then we can look up those tables in the back of our book, right? And yeah, I think you guys did these transformation or this kind of problem in the high school. So if we have a Gaussian random variable which has a mean and this variance, and then we first do the standardization, which is x minus 3 divided by 4, and this 11 is converted into 2. Okay, so this probability value can be looked up in the table shown in the back of your book. Okay, and then what about this guy? And this guy is plugged into this transformation, and then it will give -1. But in this case, please note that the direction of this inequality is a greater than. So utilizing this table, it can be computed as this value, or Gaussian random variable z less than -1. But actually this value is not shown in the book, right? The table only contains the function value of z being greater than or equal to 0, right? So we have to utilize that, right? So for this part, in this symmetric function, so we are considering the probability on this point, this part. And so this part is the same as the probability of this part. And so this guy can be represented by this one, and thus it is the function value of this. And if we have this range of an x, we do the same transformation. And then this value is -1/4, and this guy is 1. So it is it is equal to this representation, because we have the range of z greater than -1/4 and 1, right? And then from this function definition, this function definition is it's the probability it's the probability of ranging from -infinity to this 1, right? And so we can obtain this value, but also we have to obtain this value as well, because we are excluding the regions less than or negative 1/4, and so this guy can be also obtained. So we have negative 1/4 here, and then we have to compute this probability, and then this is the same as this probability, where the threshold is 1/4. And so let's see, this part is phi of 1/4, right? So this remaining part is 1 minus this value, right? So this value minus this value is obtained in this manner. Question so far? Okay, so you will often see this kind of variable, z of alpha. Okay, so this is quite an important variable, and here alpha is some real values ranging from 0 to 1. And this indicates a particular probability, okay? And then z of alpha. So let's think about alpha as alpha as 0.05, which is this case, and then z of 0.05, or this guy is our alpha. And what this means is we consider some random variable that has a particular probability density function, and this random variable is greater than or equal to this value. And then what is the probability? Okay, so we are given some particular random variable value, and then our random variable value should be greater than or equal to this threshold value, and then we can consider its corresponding probability. And then it is, in the case of Gaussian random variable, suppose this value is z of 0.05, okay? And then the corresponding probability here is this part, right? And so this value should be actually 0.05, which we give as this alpha value. Okay, so z of 0.05 means some particular random variable value, okay, and then that value is such that our random variable value is greater than that particular value, and then its probability value should be this alpha. Okay, and then let me ask the question. So 0.05 and 0.01. So which one will be bigger? Which one will be bigger? By just looking at these two. So this should be the threshold, okay? That has the probability on the right as 0.05, and that value should have the probability as 0.1, right? So that probability is larger. So correspondingly, that guy, this guy should be to the left of this guy. So we can see this relation, right? Okay, so please pay attention to this representation, because it will appear over and over in some other distribution. So if we think of the Gaussian distribution, and then we can obtain this value given a particular probability value, and then what if our random variable is maybe some Poisson random variable or some other random variable? So we can also define the exact same kind of concept, right? So that way we will keep using that kind of notion when studying some other other random variable. And in terms of the relation of this guy, and also our function phi, which is a kind of a special kind of table that we have for a standard normal random variable. By the way, standard means so normal is exactly the same as Gaussian. Okay. And why is it called a normal? Why is it called a normal? Because it's the most frequently observed probability distribution when collecting some measurement or some observation data in real world. So suppose we collect a person's height, okay, and then we can think of its histogram, right? And that histogram is approximately the normal distribution. The probability density function will look like, will follow the normal distribution. With the particular mean and variance value. And also, if we collect maybe a person's weight or a person's life expectancy, like how long he or she lived, and and things like that. And those data are usually following the normal distribution, because it's frequently observed patterns for the data existing in our real world. So that's why we call it as a normal distribution. And then standard means it has a zero mean and unit, or the variance is 1. So that is the meaning of this standard. Okay, and then So this phi, so the definition of phi is, this guy is the probability of, random variable ranging from minus infinity to 1.645, right? And this guy should be, some distribution and some value here, and then we are considering this probability, but in this notation we consider the opposite probability, and this probability should be 1 minus alpha if we are given alpha. So if we are given it as 0.05, and then this probability should be 0.95. Okay, so that is this 1 minus alpha, and so so if we move it to the other side, and then we obtain this value. Okay, so this particular value is this value. So that means if we have a standard normal random variable at 0.1645, these probability will be just 5%. Okay, and then what about this? This probability is 2.5%. In that case, this value is approximately 2, or 1.96. Okay, and we can think of the standard deviation and its multiples as possible ranges of our random variable x. So if our random variable x, centered with its mean, if it is it has the range of negative sigma or positive sigma, and then this range has the probability of 0.68 and things like that, 68.3, right? And then if it is approximately like a plus minus 2 sigma, then the probability will be approximately 95%, and then 3 sigma width, and then it will have 99%, almost 100% of the probability. And the normal random variable has some characteristics or some properties. So if it is transformed with this function, which is just scaling the original random variable, and we add it with some constant value, and then this one will also have the normal distribution, and then the mean will be shifted or transformed with respect to the same transformation, and then the variance will be scaled by this scaling factor alpha squared. So is it always true for other random variable? So let's think about this transformation. And then suppose the mean of an x is mu, and the variance of an x is sigma squared. And then we know mean of y is a mu plus b, and the variance of y is a squared sigma squared. So far so good. It is always true regardless of the distribution that x has, right? But even though these are true, we do not know, or we cannot guarantee that this random variable y also follows the same type of distribution. So if it was maybe some other types of random variable, then after this kind of transformation, the distribution may be quite different types of random variable. So if we started from Poisson random variable, and then if we transform our variable in this manner, then the resulting variable may not follow the Poisson random variable. Okay? But in the case of Gaussian random variable, it will maintain the same type of a random distribution of this normal or Gaussian random variable. Okay, so this kind of linear kind of transformation will just maintain the same probability distribution type, which is a Gaussian random variable. And also, if we add these two Gaussian random variable, and then these added ones will also follow the Gaussian random variable. And if they are independent, and then so you guys remember the formula. So what was this formula? And what? Whereas x1, x2, and right? And so this is an additional term, but if we have an independent random variable, and then this guy is 0 because e of x1, x2 is equal to e of an x1 times expectation of x2, right? Okay. Yeah, so let's just think of it a little bit more. So let's think about some dependent case. Let's see. And let's think about this case where we have a really high correlation coefficient, which means, they are not independent, right? And why is it not independent? I mean, we are just reviewing what we learned. So the marginal distribution of x, for example, so let's see. Let me add the page. Okay, so what is the marginal distribution over x? It is approximately something like this. And why? So if we just project it down to x-axis, okay, and then roughly this region will have a dense kind of area, right? So that means if we think of some kind of histogram, and then we will have some kind of mountain, kind of peak around that point. So this is our marginal distribution, and then we can also think of this marginal distribution over y, and that marginal distribution, or f of an x, regardless of y, okay, that should remain the same as some conditional distribution. For example, y equals maybe 1, or y equals 2, or something. So in all cases, when fixing y as a particular value, that should be the same as this guy, right? And then let's fix the y value. If we fix the y value, I'm going to fix y as around 80. And we think of this range, right? And then what about the distribution? I mean the conditional distribution of x given that particular y value. And it will be something like, so if we think of the projection value, and then those will not be projected onto the x-axis because that will not follow, that is not satisfying the y as this particular value. So they have a different y values here. So yeah, so it's a little bit approximate sense, but yeah, around these y ranges of on y, so data are centered or kind of densely located around that region. So the distribution is something like this. But if we recall the marginal distribution, then it was something like this, right? And if we set y as a higher value, then its conditional distribution will be different, right? So that's why this guy is not a independent. But what about this case? Just chunk of data point. Just chunk of data point. And in this case, if we do the same thing, we can think of some marginal distribution and then some conditional distribution at the different particular value of y, and then the distribution should remain the same, right? The mean and the variance and the shape itself should exactly match. So that is the meaning of statistical independence. And then now back to our case where our random variable is defined by x1 plus x2. So this is an x1 and this is x2. And then what is this random variable? What is this random variable? Okay, so so this value and this value. So yeah, what I'm trying to say is this y plus x1 plus x2 is approximately like placed along this axis. Yeah. So it is a little bit tricky to explain. I mean, more trickier than I thought. But yeah, if we follow if we consider the variance along this axis, okay, because that is x plus y, and then in this case, the variance will be really maximized along that direction, and the variance along that direction is greater than, it's larger than the sum of individual variance of these x and y. And so it has a little bit, additional boost from this addition. So that kind of additional boost is, revealed by this term. Yep. But anyways, let's go back to this example where we have an independent random variable, and it's still a Gaussian. In the case of this, the sum of these two random variables, and then the mean and the variance will be shown in this form, just because they have zero covariance term. Yep. I think we can skip this example where we can consider this x1 plus x2 as a new random variable. So it's just simple because it's still a Gaussian, and then the mean value is the sum of the mean of these two random variables, and also the variance are also the sum of these two random variables variance. Okay, then next, we revisit the binomial random variable, and this guy can be approximated into the normal distribution. So, this is not from the book. I borrowed this from some other slides, but it's a probability distribution, which is a clearly first of all, this binomial random variable, is this discrete or continuous? It is discrete or continuous? is a binomial random variable. Is it a continuous one or the discrete one? It is discrete, right? Because it's a count, right? So it's only an integer. It cannot be like a 1.3 or something like that, right? And so, yeah, although we drew this distribution as this line graph, but you can think of like this kind of bar graph, which is a kind of discrete kind of probability function. And in this case, we draw this probability function for binomial random variable, but we fixed p as this value, and we increased the number of trials. And then if we increase this number of trials, and then yeah, this shape will look more and more like a Gaussian random variable. And also, if we fix n in this point, in this case, but we vary or we change the p-value, and then if p is not too small, and then the center or the mean value will be placed around the center, ranging from 0 to the maximum value. Okay, so what is the maximum value in this case for our random variable? It will be 100. So 100 is a possible maximum value of our random variable. And so between these ranges, so this curve will be more like a symmetric Gaussian curve. Okay, so so n gets larger and larger, and then in the case of probability being not too small or not too big, and in that case, this one will look like a Gaussian random variable. If p is too small, and then its mean value or its peak will be really biased towards the 0 or the maximum value. And once we can approximate this binomial random variable into a Gaussian random variable, where n is really large and p is not too close to either 0 or 1, then this binomial random variable gets close to this normal distribution, where the mean value is still the same as the mean of this binomial random variable, and also the variance as this guy. So we keep the same mean and the variance, but the shape itself will look more and more like a Gaussian. And then if we follow this Gaussian random variable, and then if we transform this as a standard normal distribution, and then this guy will follow this standard Gaussian random variable. And and binomial, so sorry for the Korean, but it's a binomial, okay? And this is Poisson random variable. And we studied that Poisson random variable is quite related to binomial random variable, right? And so when are these approximately the same? So we had some condition where n is really large and p is really small, close to 0, but n times p, which is our mean value or expectation, remains as some constant, okay? And that constant, so it shouldn't go to infinity or it shouldn't go to 0, so we cannot consider this case, okay? So this guy is maintained as a fixed constant, and then that's when this binomial random variable is approximately the same as the Poisson random variable, okay? And then as I mentioned, a binomial is approximated into this normal distribution or Gaussian random variable. So approximately the condition for this approximation being possible is this NP, which is our mean value. Okay, mean value being larger than, for example, 5. Okay, and then this variance is also greater than 5. So that means, so what if this mean value is smaller than 5? Smaller than 5. And in this case, yeah, the binomial random variable, the range of the possible value will always start from 0. So we cannot have the probability on this side when x is negative. So we cannot have such kind of probability, but NP is yeah, quite small, like 1 or 2 or something, and then it will be really skewed distribution. So it wouldn't, yeah, it will not look like a Gaussian distribution. So we have to put our mean somewhere a little bit far from the 0 or origin, and that way we can obtain this Gaussian kind of like shape. And yeah, similarly, in the case of personal random variable, if lambda is greater than 5, and then we can kind of approximate it to normal distribution. So this is a normal distribution. Okay, and then similar to this binomial case, we can draw this personal random variable's probability function, and then lambda being 1, 2, 3, 4, 5, and then yeah, it has more and more similar shape to Gaussian random variable. And yeah, in this shape, let me ask the question. So among the 4 cases, which one has the largest variance? Which one is the largest variance? Which one is kind of widest one? So widest one is this guy, right? And what would be the variance then in this case? So personal random variable has an expectation or the mean value as lambda. And what about the variance? Variance was the same, right? So variance should be lambda too, and lambda as well. And so variance is proportional to the mean value, and that's why, yeah, we obtain a wider and wider distribution. But still, it's similar to, it's getting closer to the normal distribution in terms of its shape. That corresponds to the parameter of mean and the variance as the same value. Okay, and then the next distribution. So now we, starting from uniform and this Gaussian random variable, and also this guy as a exponential random variable, all of them are continuous random variable, right? So this is one kind of continuous random variable. Okay, so exponential random variable has this kind of shape, as a probability density function. So it is defined by this formula. If x is a non-negative value, but x is negative, we assign 0 density value. So if our random variable follows this density function, and then we call it as a exponential random variable. Okay, then let's think about some probability function here, where x is less than or equal to x. Okay, so this function is defined by this, and then if we compute this integral, then it will have this, right? And then what about the probability of this? What about the probability? So it will be 1 minus this guy. So it has this kind of simpler formula. Okay, and what is the physical meaning, and when is this exponential distribution is used? In practice, you can think of some kind of counterpart of a distribution. Against the personal random variable. Personal random variable was the number of events happening, right, within a certain time range, right? So how many customers will visit within an hour, right? And on average, we see maybe five people visits maybe our convenience store within an hour. And then 5 will be our lambda, the average number of visitors and so on, right? And then internally, n and p, n should be really large. So if n was 60 and then 1 unit time was 1 minute because we considered 60 minutes, and then p, which is the probability of that particular event happening, I mean the customer visiting, that probability is considered as p, right? And so since the time, unit time of 1 minute is really small, and thus p gets small, but when considering 1 hour, the number of n, n times the unit time. So if this unit time is smaller, and then n will be larger and larger. Okay, so that was a story of a personal random variable. And then exponential random variable is a kind of a opposite thing to this personal random variable, because it's actually the distribution of waiting time of the next customer. Okay, so suppose one customer just visited our convenience store, and then what will be, how long should we wait until we meet the next customer visiting our store? Okay, so of course, in the case of a previous personal random variable, was it a discrete or a continuous one? Was it continuous or discrete? Personal random variable, what was it a continuous or discrete? So it was basically a count, right? So it was an integer value, so it was discrete one, right? But in the case of a exponential random variable, it's just a waiting time, right? The waiting time is the real value, so it is continuous one. Okay, and then just having the relationship to the personal random variable in mind, and it has a similar parameter of lambda. So you can think of this lambda as having exactly the same meaning as the personal random variable parameter, which is the number of customers visiting within a certain amount of time, right? And then suppose in 1 hour, on average, like 3 people visit our store. And then what is the average waiting time of waiting for the next customer just right after one customer visited? It is 1/3 hours, right? Because 1 hour we visit, 3 customers visit, and then the average waiting time is just 1 hour divided by 3, right? So this guy is our mean value of this exponential random variable. So here we see lambda, and it's not a coincidence. It's a kind of intentional kind of reuse of this same parameter lambda, because they have the same meaning. Okay, so this guy, you can think of it as still the average number of customers visiting our store within an hour, and the mean value or the average expectation value of this random variable, since it has the meaning of average the waiting time, the average waiting time will be this guy, 1/lambda. Okay, and this is actually 1 hour. But what if we consider like a 3 hour? It actually doesn't matter. 3 hour is considered as one kind of unit time that we are interested in, right? So this time range, this time duration, we consider this a fixed or particular amount of time range and that is considered as 1 unit time. And so, yeah, so that is kind of 1 unit time. Yep, and then we simply divide this unit time by the average number of customers visiting our store. And what about the variance? Yeah, we cannot prove it because we skipped a moment generating function. But yeah, let's just take it as granted, yeah, without worrying too much about the proof. But yeah, it's a variance as this guy. And one really interesting property of this exponential random variable is this memoryless property. So since it is quite interesting, I just copied and pasted almost the entire page to our slide. Okay, so the meaning of it is something like this. So let's think of the hardware failure. So yeah, I'm not sure about you guys, but at least in my case, I'm kind of worried. Yeah, I'm kind of afraid of potential kind of a malfunctioning or a defect of my hard drive because it contains a lot of my precious stored data, right? And then, yeah, suppose you bought your hard drive just today, and then you hope it lasts for 1 year, right? And then here, the event of an interest is the hard drive starting to malfunction. So it just stops working, right? It just goes wrong. So that is the event of an interest. And then the average time that this event will occur will follow this exponential random variable. Okay. In that case, if it is yeah, if it fails maybe 3 times per year, for example, okay, 3 times per year, and then we can expect on average, like within like 4 months, it will go wrong, right? Because 1 year divided by 3, which is 4 months, right? And then we can think of this situation. So we bought our hard drive today, and then we can think of the probability of it starting to malfunction. Okay, so what is the time? Okay, what is this waiting time and their distribution? If it follows an exponential random variable, and then let's think of some other situation. So after maybe 6 months, it lasted. It lasted with no problem. So it just worked with no problem until 6 months. And then starting from that day, what will be the probability of this hard drive lasting for maybe 4 months? Okay. So the probability of the hard drive lasting for 4 months starting from the first day, and then the other case is the probability of this hard drive lasting for 4 months after 6 months of use. So we bought it on the January 1st, and then it lasted like until this date. So what is the probability of it? And then the other situation is it lasted until July 1st, and then it lasts until November 30th. Then what is the probability of this case and this case? So magically, these two probabilities are the same. Okay. So here the situation is, in this case, we feel like it will have a larger probability of failing until this 4 months period, because we already used it for about 6 months. So it may go worse and worse, and thus it's getting closer to like a malfunction. But the reality, or this, if it follows exponential random variable, and then the probability of this case and this case is actually the same. So that is called this memoryless property. So yeah, it has a really nice yeah, no need, yeah, so there is some sentence like, there is no need to remember the age of a functional item, okay, which is like, okay, it lasted until today, it lasted like 6 months or even like 10 years and so on. So we don't need to remember it. Instead, it will just still functional as it is just as good as new. So the hard drive that was used for 6 months, and also the hard drive that you just bought at that same day as a new drive, okay? So those two drives will have exactly the same probability. Okay, so let's just represent it by using the formula or mathematical expression. So the definition of this memoryless is as follows. So the probability x being larger than s, which is like 4 months, and then the probability of x lasting more than 4 months is actually the same as it lasts more than 10 months given x lasted 4 months. Okay, so yeah, pay attention to this part. So we know, or we assume that happened, which means we know that this hard drive somehow lasted for 4 months. Okay, and oops, yeah, it should be 6 months. Sorry. If it lasted for the first 6 months, and then the probability of lasting 4 additional months is the same as the brand new one lasting for more than 4 months. So this is the point. So let me see if we have some exponential. Yeah, unfortunately we don't have the exponential. Let me see if I can find the function shape. Okay, so the function shape is really simple. Right? It is an exponential distribution. Okay, and then so if it lasts for more than 4 months, and then the corresponding probability will be here, right? And then if it is lasting for more than 10 months, it will correspond to this probability. So those two probabilities will clearly not be the same, right? But here the situation is this conditional situation. So among this entire region, the probability of this region, okay, that probability is actually the same as when considering the entire region as this part and the relative ratio of this region. Okay, so this is this can be understood as our conditional probability, right? So let me try to give a more specific example. So what is the entire area? It is 1 because it's a probability density function. And then suppose this part as 0.7. Okay, so suppose the probability of it lasting for more than 4 months is 70%. And what should be this part? What should be this part? It should be 0.49. Okay, in this case, this kind of probability, when considering kind of an unconditional situation. I mean, there is no condition, but if we are conditioned that it lasted for more than 4 months, and then this 0.7 will be our entire universe, and then the probability of this particular part, with respect to this as our universe, and then these two ratio will be always remaining as the same. So this is the meaning of this memoryless property. Any questions? Okay, let me further manipulate this equation or this formula. So now we understand this is a memoryless property. Okay, and let's just write this left-hand side as like this: P of x greater than t, and P of x greater than s plus t, and x greater than t, right? So this is the basic formula of P of maybe b given a, and then it is P of b and a and divided by P of a, right? So I just wrote this formula here. Okay, and then this guy is written here, and let's think about this. So it is the event that satisfies both of these conditions. So x being greater than s plus t and x greater than t. So t was 6 months and s was 4 additional months, right? So those two events is actually like this kind of relationship. So this event is a larger event, so that that contains this smaller event. So intuitively, if it lasted 10 months, and then it's obvious that it lasted 6 months, right? Because if it didn't last 6 months, and then it cannot live, it cannot last 10 months, right? So we can safely omit this part and then just leave the keep the more strict condition just only. So the numerator will be ending up with this formula, and then what about the denominator? We had this denominator, and this denominator is moved to to the other side, and then we obtain this. So let's try to interpret it. So the probability of x, this hard drive lasting for 4 plus 6 months, which is in total 10 months. And then the probability of this event is actually the product or the multiplication between these two probability value of this guy lasting for more than 4 months and more than 6 months. Okay, and then why is it true? Because it had really simple probability of this. So if x is the probability of x greater than this small x value, it is just having a simple mathematical expression. Okay, so if x was 10, and then it was this, and then it is of course 4 times 8, so like this. Okay, so this is called a memoryless property, which is quite interesting. Then it has some other interesting properties. So let's consider an independent exponential random variable, which means so we have maybe we bought maybe 10 different hard drives. Okay? 10 different hard drive, and then it will have its own average time of failure. Okay, so every time taken in the failure. So this hard drive is a little bit cheaper one. So it on average it will fail within maybe on average it's like fail in 4 months, and it's like 8 months and so on. Okay, but still this if it is 4 months, and then the lambda 1 should be 1/4, right? Because we have a reciprocal relationship. So lambda is the average average number of events occurring, and average time is a reciprocal of it. And if we have this multiple independent exponential random variable with its own parameter, and then suppose this kind of function of these random variable. So it's a mean value. So we bought 10 hard drive, and then we consider the earliest possible time that at least one hard drive start to fail. Okay, so we just look at the 10 hard drive, and then we monitor, and at least one of them, the first one actually started to fail, and then we count or we measure that amount of time. Okay, so that is this function. Okay, and then we can interestingly represent it as this kind of probability, and it means the minimum value of these as this particular x value. So let's say it is 5 months, and all of them should be more than like 5 months, right? And that probability from the independence, we can just compute, or we can just multiply all of these individual events, right? And then this event were conveniently represented by this one e to the power of negative lambda I times x, and then we can just simply sum them up in this exponent part. Okay, so we have some straightforward example that I can skip, I think, and then let's wrap it up today, and then continue from this chi-square distribution next time. Thank you.
fx가 이런 가정이라는 거 아니고 이렇게 다 있는데요. 이걸 왜 하는 거죠?
이게 왜 하냐면 이게 이제 모멘트 제너레이팅 펑션이라고 해갖고 이거를 유도를 해놓으면요, 이거를 이제 미분을 어떻게 한 번 하고 두 번 하면
이게 뭐 EX 발전해서 X 되는데 왜 그러니까 이 과정이 넘어가는 과정이
이게 우리가 스킵한 3장이었나 어딘가에 그 모멘트 제너레이팅 펑션을 뭐 이렇게 쓰는 게 있어요. 이거를 어떻게 유도를 하느냐, 그 익스펙테이션 파트에 나오는 거 한 3장인가 4장인가 있어요. 이게
스킵한 건가요? 네. 그러면 이거는 그냥 이러려니 하고 넘어가는 거예요?
이거 과정은 몰라요.
여기 뒤에 부분만 이해하면서
여기서요 이잖아요.
네.
근데 랜덤 베리어블을
네.
하나의 랜덤 베리어블 여러 개 가면서 이거는 거 아니에요?
하나의 랜덤 베리어블이 그러니까 이게 예를 들면 하드 드라이브를 내가 시게이트 거를 샀고 내가 뭐 히다치 거를 2개를 샀다. 나도 이렇게 2개를 사고요. 또 다른 사람도 2개를 또 산 거예요. 그래서 이 한 조합, 얘는 얼마 만에 페일이 났고 얘는 또 얼마 만에 페일이 났고, 그게 나의 랜덤 베리어블, 페어드 랜덤 베리어블 혹은 조인트 랜덤 베리어블이고, 또 한 사람이 또 그렇게 똑같은 조합을 샀는데 그 사람은 또 운이 좋아서 뭐 좀 오래 가고 뭐 이런 것들이 한 페어가 이제 랜덤 베리어블인 거죠. 조인트 랜덤 베리어블.
그러니까 이게 그 여러 개 했을 때 그거요.
네, 하나하나의 하드 드라이브의 어떤 그 페일리어가 나올 때까지 타이밍.
그리고 여기서요.
네.
아까 이거 숫자 그냥 해가지고 했잖아요.
네.
좀 이해가 안 되거든요.
네네네.
예를 들어서 여기가 4고 여기까지 0.7이라고.
어디가요? 요만큼?
아니요. 이게 요만큼.
그만큼? 네.
그러면은 이게 0.7이면은 여기 10에서 14까지 가는 요 뭐라 해야 되지?
네.
요 부분에 요거가 0.7이 돼요.
아, 그러니까 이게 이쪽 오른쪽으로 가는 프로바빌리티를 생각하면 좀 더 편하고요. 그러니까 이제 4개월 이상을 산다 그러면 4개월 이상을 산다 그러면 이렇게 돼 있으면 여기가 4라 그러면 이게 확률인 거잖아요.
아, 예.
그렇죠?
예.
그러니까 여기가 예를 들면 0.7이래요. 그럼
예.
여기는 뭐 0.3인 거죠. 근데
예,
이거는
예.
우리는 직접 뭐 관심이 뭐 있지는 않고
예.
네. 이게 전체 중에서 0.7인 거고요. 여기가 이제 4였잖아요.
예.
여기서 뭐 예를 들면 한 점을 10을 잡죠.
예.
10을 잡으면 요만큼 중에서 4를 더하면 14가 나오겠죠.
예.
그러면은 요 10 이상부터의 요 확률 중에 14부터가 차지하는 그 확률의 비가 0.7이라는 뜻이에요.
아, 예.
이게 컨디셔널 프로바빌리티니까.
아, 예.
네.
아, 근데 저 출석 몇 번한테 좀 확인 좀 할 수 있어요.
이름이 뭐예요?
신광
네?
신광 롤이요.
어디 있을까요?
그 앞쪽에 있을 거예요.
그래요?
그 여기서
여기.
아, 예.
괜찮아요. 네.
아, 없어요?
빠진 적 있었어요?
아니, 저 첫 주에 안 와가지고.
그럼 체크해야겠네. 네.
저희 두 번째 과제 언제?
곧 내줄게요. 네.
추석 끝나고
추석 끝나고요. 추석 때 공부도 좀 해야죠.
추석 때 나와요?
네. 네. 그게 나중에 또 밀려서 또 어차피 또 뭔가 해야 되는 숙제의 총량이 정해져 있다라고 생각하면. 네. 근데 데드라인은 추석 바로 다음 화요일은 아니고 그렇지 않도록 할게요. 네.
감사합니다.
네.
되게 질문 좀.
네. 네.
이게 너무 제가 생각하기엔 특별한 케이스인 것 같은데
네.
이거를 왜 굳이 지수 확률 변수라고 이름 지었어요?
그냥 이름 자체는 이게 지수 함수로 되어 있는 거라서
그래서
이렇게 붙였고요. 네. 그리고 이게 또 마이너스를 붙인 이유는 이게 항상 좀 떨어지도록 해야 지수 함수 이렇게 완전히 폭발적으로 증가하는 애 있잖아요. 그래서 이제 떨어지도록 이렇게 좀 만든 거고요. 그러니까 결국은 이에 이제 마이너스 램다 x를 했다는 거는 뭐 이게 이제 양수이기만 하면 이게 기본적으로 이게 밑이 이제 1보다 크잖아요. 그러니까 여기 마이너스 있으니까 이게 기본적으로 뭔가 하여튼 뭐 3분의 1의 뭐 x승, 뭐 램다 x승 뭐 이런 식인 거예요. 그러니까 뭐 기본적으로 이렇게 좀 밑이 1보다 작은 숫자에서 x가 증가함에 따라서 쭉 가는 함수인 셈이죠.
궁금한 게
네.
이 앞에 이산확률 변수까지는
네.
뭐라 해야 되지? 특별한 저희가 유추 가능한 사건에 대해서 적용할 수 있잖아요. 뭐 딱 이항 분포라든지 뭐
네.
베르의 분포도 그렇고
네.
사건이 딱 앞면 뒷면으로 흑백으로 나눠지는 거에 대해서 적용을 할 수 있다고
네.
생각할 수 있는데 연속 확률 분포는
네.
저희가 어느 상황에서 뭘 써야 되는지 어떻게 판단할 수 있어요?
그게 좀 아주 잘은 모르겠는데 그냥 이런 사건들, 그러니까 뭐 뭔가 고장이 나는 확률이, 그러니까 시간이라든가 이런데 보통 이런 확률 분포를 좀 비슷한 모양으로 좀 따르더라.
따르는 거를 이제 찾아가지고
그렇죠.
쓰면 돼요.
네. 맞아요. 그러니까 대략적으로는 이런 상황에서는 이런 현실 상황에서 뭔가 고장 나는 시간이라든가 이런 거에 해당하는 확률 분포는 의미상으로 볼 때 뭐 익스포넨셜을 따르더라. 그러면 이제 그런 거를 알아서 쓰거나 아니면 그런 게 이제 뭐 문제 이제 이거를 정확하게 따른다고 이렇게 주거나. 이게 아까 이야기를 안 했는데 이제 익스포넨셜은 이렇게 계속 지금 봤듯이 이렇게 계속 떨어지기만 하는 함수잖아요. 그래서 이 말은 뭐냐면 좀 그런 거예요. 그러니까 하드 드라이브를 처음에 샀는데 고장이 처음에 좀 안 났어요. 그러면 끝까지 간다고 이런 셈이에요.
그것도 완전 이상적인 거 아니에요?
네?
그러니까 여태까지 열심히
네.
썼던 거랑
네.
지금 새로 사는 거랑 분명히 차이가 있는데
네.
그것도 공통적인 건데 좀 아예 독립적인 거예요.
그러니까 그게 이제 그러니까 좀 나도 직관적으로 좀 뭐 약간은 좀 직관에 반대되는 것처럼 느껴지기도 하는데 기본적으로는 이제 뭔가 10시간 그러니까 뭐 열흘을 이렇게 살아남았어요. 그러면 그 다음 날에 이게 뭔가 고장 나겠지라는 어떤 그런 걱정은 뭔가 첫날에 이걸 새로 사서 다음 날엔 설마 고장이 나겠어? 근데 그때 확률이나 똑같다 뭐 이런 셈이거든요.
저기서 람다가
람다요?
람다라는 모수는 계속 저희가 앞으로 쓰는 거예요.
람다라는 파라미터요?
네.
이게 이제 정해져야지 돼요. 네.
람다가 뭐예요?
네? 람다요? 람다가 그러니까 이제 이거 람다분의 1이 이게 평균적으로 고장나는 어떤 값이라고 생각하면 돼요. 그러니까 람다를
이렇게 잡은 거죠.
네, 그런 파라미터로 잡은 거예요.
그럼 저기서도 2 마이너스 람다 x잖아요.
네.
두가.
네.
그럼 그것도 0부터 무한대까지 하면 1이 나와요.
네, 그렇죠. 그 노멀라이즈를 해주려고 한 게 여기에 붙어 있는 요 램다가 여기 있는 거예요. 그러니까
그렇게 해야지.
네, 그렇죠. 요것만 해갖고 이거를 0부터 그러니까 0 이하로는 우리가 정의를 안 한 거고 0부터 무한대를 이거를 하면 뭐 적분해 보면 이제 어떤 값이 나오는데 그건 1이 아니고 그걸 1로 맞춰주기 위해서 값이 뭔가 같은 이거예요.
한 4장의 문제 풀 때 보니까 저런 확률 변수 나오더라고요. 근데 항상 람다랑 저게 마이너스 람다랑 똑같아요. 그리고
네.
저 이거
네.
통계 공부하는 게
네.
머신러닝 공부할 때 도움이 되나요?
머신러닝이요? 아, 네, 도움이 돼요. 근데 너무 열심히 해두고요. 네. 안 되는 부분도 많고 되는 부분도 많고. 네. 그러니까
보니까 막 선형 알고리즘밖에 안 쓰는 것 같은데.
네, 뭐 나도 개인적으로는 이제 선형 대수가 훨씬 더 많이 쓰인다라고 생각을 하고 네, 그렇게 생각을 해요. 그러니까 그 확률에서 내가 생각할 때는 이런 여러 가지 특정 디스트리뷰션을 우리가 배우잖아요. 뭐 카이 스퀘어는 아니 그건 뭐 익스포넨셜, 뭐 포아선 이런 걸 배우잖아요. 근데 솔직히 나도 이거를 과목을 지금 작년부터 이걸 어떻게 해서 가르치고는 있지만 그런 거 잘 사실 좀 모르기는 잘 몰라요. 그리고 참고로 나도 뭐 머신러닝 쪽을 하거든요. 그래서 근데 잘 공부해 두면 좋고 전반적으로 보면 그런 확률에 관한 기본 개념 있죠. 아까 컨디셔널 프로바빌리티나 뭐 이런 뭐 조인트 랜덤 베리어블이나 아까 마지널 디스트리뷰션이나 뭐 그런 거에 대한 좀 개념이라든가 뭐 그거에서 나오는 코베리언스 및 코릴레이션 이런 것들은 굉장히 좀 유용하게 쓰이고요. 그런 것들은 아주 직관적으로 탁 좀 잡아두는 게 좋고 그 다음엔 또 일부 경우 이제 뒤쪽에서 나오게 되는 그 하이퍼시스 테스트 가설 검정 뭐 이런 쪽이 실제 머신러닝이나 뭐 어떤 기타 내가 뭔가 연구를 해서 실험을 했을 때 그게 진짜 뭐 3% 내가 성능을 올렸는데 그냥 올렸으니까 좋죠 하고 끝나는 게 아니라 그게 뭔가 통계적으로 유의미하냐 뭐 이런 것들을 조금 더 분석을 해주면 훨씬 더 좀 그래서 그런 쪽에서 공부도 또 필요할 것 같고 근데 그게 거의 약간은 이쪽에서의 조금은 끝판왕처럼 그쪽에서 나오거든요.
끝판왕이요.
네, 약간 그래요. 그러니까 지금 중간 것들이 그쪽에서 좀 나오는 거예요. 다. 그래서 좀 힘들고 좀 답답할 수도 있고 뭐 그렇긴 할 텐데 거기까지 가보지 않으면 그 전에 내가 지나왔던 길 중에 뭐가 필요했었고 안 필요한지를 잘 모르거든요. 그래서 약간은 좀 그 곰이 저기 뭐 이렇게 뭐 100일인가 뭐 며칠 있다가 갑자기 사람이 됐듯이 약간은 그래도 좀 배우는 것들이 좀 지루하거나 재미없는 것들도 이 5과목뿐만 아니라 좀 공부를 하는 과정 중에 나오더라도 좀 잘 해주세요. 그러면 진짜 공부해서 남주나 이 말이 진짜 좀 틀리지 않아요. 네. 그러면 뭐 열심히 해라 이거예요. 네. 네. 네.
아까 여기서 이 리니어 트랜스포 할때
네.
사실은 이게 이렇게 되면
네.
무조건 이게 되잖아요.
그렇죠. 이거는 맞아요.
근데 어떤 걸 보장이 안 된다?
어떤 거 보장이 안 되냐면 그러니까 x가 가우시안이에요. 근데 y가 가우시안인지는 모르는 거예요. 네. 그러니까 가우시안이다라는 얘기는 그러니까 얘네 저기 디스트리뷰션이 요구하는 파라미터만 맞으면 어떤 그 정확한 그 모양을 따라야 된다는 거잖아요. 네.
그럼 당연히 안 되겠네. 선형 변화한 거면은 이 그래프
네.
자체가 바뀌어버리는데.
뭐 그렇죠. 그런 셈이에요. 근데 가우시안은 그게 유지가 된다는 거고
아, 가우시안 x 가우시안일 때
네.
y가 가우시안인 거는 보장이 된다 이거.
그렇죠. 네.
보장이 되는데
네.
만약에 다른
경우는 일반적으로 안 된다 이거예요.
다른 만약에 분포 예를 들어
음.
포화송이나
네, 뭐 그런
이런
것들.
익스포넨셜
그렇죠.
것도 다 안 되고 그런 거는 일반적으로 안 되고
그렇죠.
어떤 특정한 게 맞아 떨어지면 그게 될 수도 있는데
그렇죠.
일반적으로 안 된다
네.
이런 말.
그 익스포넨셜은 또 되긴 돼요.
익스포넨셜.
이거는 워낙 간단하니까
아,
해보면 이제
근데
이제 ax 플러스 b로 되면
네.
이거는 이 상수 쪽으로 빠지고요. 그렇죠?
아,
이 b는 이 상수 쪽으로 가고 그 다음에 이
어차피
x는
A도
a는 요거랑 이제 붙어서
네.
새로운 람다를 만들어내고요. 네. 그래서 이거는 다시금 익스포넨셜 디스트리뷰션으로 되고요. 안 되는 게 뭐가 있을까요? 뭐 있을 텐데. 일단 디스크릿은 좀 되기가 힘들고, 왜냐면 포화송이 뭐 예를 들면 0부터 1 뭐 이런 정수를 가졌는데 뭐 벌써 y는 3x만 해도 그러면은 이게 이상해지잖아요. 그러니까 0이 0으로 가고 1은 3으로 가면 2와 1, 2는 어디 있냐. 이거 해당하는 확률은 그러니까 없는 셈이거든요. 네, 네, 이런 건 안 되고, 그리고 컨티뉴어스에서도 뭐 안 되는 것들이 좀 있겠죠. 나도 이게 지식이 짧아서 지금 탁 명확하게 그건 없는데, 뭐 우리가 배웠던 확률들 중에 뭐 해보면 안 되는 게 분명히 있을 거예요.
그리고 이거 이제 코릴레이션 코에피션트랑 이제 인디펜던트 낫 인디펜던트 할 때
네.
그러니까 이제 R 값이 그러니까 1에 가까워질수록 이제 인디펜던트라고 말하기 좀 힘든 거잖아요. 근데 이제 그걸 설명해 주실 때 이 점값들을 갖다가 이제 x축으로 다 이렇게 뭐 내린다고 하시는데
네네네.
근데 이제
네.
제가 생각해 본 거는 사실은 뭐 예를 들어서 R이 이제 극단적으로 1일 경우에는 이렇게 되잖아요.
네.
근데 그걸 이 점을 갖다가 다 내린다고 하면 그냥 이렇게 쭉 이렇게 되는데 그거랑 이제 나 이렇게 그
네.
분포를 그려주셨는데 그게 사실 이해가 잘 안 돼가지고
네. 정확하게 선형성을 따르면 그러니까 점이 이 라인을 따라서 분포를 하고 있는데 이게 x와 y가 어떻게 분포를 하고 있는지는 잘 그러니까 다 상황마다 달라요. 여기 한 점, 여기 한 점, 여기 막 굉장히 밀집되어 있다가 또 이렇게 뜨문뜨문 이렇게 될 수도 있죠. 그렇죠? 그럼 이때 마지널 디스트리뷰션은 사실 뭐 이렇게 되는 거예요. 근데 꼭 이렇지 않을 수 있어요. 뭐 여기에 밀집이 막 돼 있고 여기에도 또 막 밀집이 돼 있어요. 그러면 마지널은 뭐 이렇게 나오겠죠. 네. 근데 중요한 건 y가 어떤 값, 이게 이제 마지널이고 y가 픽스가 됐어요. 그러면 y가 픽스가 됐다라는 말은 이렇게 굉장히 extremely, 그러니까 correlation coefficient가 1인 경우에는요, y가 픽스되면 그거에 해당하는 x도 픽스란 소리예요. 그죠?
네.
그럼 이때 컨디셔널 디스트리뷰션은 뭘까? 그냥 이거예요. 이 값에서만 확률이 1이고 나머지 싹 다 0인 거죠. 그러면 얘가 가지는 마지널 디스트리뷰션과 이 컨디셔널이 전혀 같지 않죠. 네. 그리고 좀 약간 이렇게 조금 좀 지저분하게 분포를 하고 있다. 그러면 예를 들면 여기서 이렇게 잘라요. 그러면 y가 이 값일 때는 대충 디스트리뷰션이고 이렇게 나오는 거예요. 그러니까 뭐예요? 그 y가 이렇게 쭉 가면 x의 디스트리뷰션도 이렇게 됐다가 점점점 이쪽으로 좀 쉬프팅이 되겠죠. 그러니까 쉬프팅이 된다라는 것도 중요하지만 기본적으로는 디스트리뷰션 자체가 아예 다르니까 y 값에 따라서 x의 디스트리뷰션이 쭉 뭔가 이동을 하게 되니까 저기 디펜던트하다.
근데 이제 만약에 그런
네.
거의 랜덤
네, 청크로
돼 있으면은
그렇죠. 막 돼 있으면 이거에 그냥 마지널을 내려서 본거나 아니면 이렇게 내로하게 밴드를 잘라서 요만큼에 해당하는 애들, 또 요만큼에 해당하는 애들, 또 요만큼에 해당하는 애들을 보면 다 원래 디스트리뷰션과 똑같아집니다.
그러니까 이제 고정했다라고 한다면은
Y가
해당하는
고정했으면
게 이렇게
있을 텐데 걔네들만의 디스트리뷰션을 따지면
디스트리뷰션이 따져도
원래 거랑 똑같다는 거죠. 그러니까 이런 동그랗게 생겼다. 동그란 건 될까를 따져보면 여기를 이렇게 자르잖아요. 그럼 이거는 굉장히 와이드해요. 요 끝을 이렇게 잘라요. 그럼 이거는 되게 이제 네로하죠. 이것도 거꾸로 코릴레이션 코에피션트는 0일 수 있지만
그런 거
네, 인디펜던트는 아닌 거예요. 그러니까 인디펜던트 하면 그거 코릴레이션 코에피션트가 0이지만 거꾸로는 아닌 거예요. 또.
인디펜던트 하면
네. 네. 인디펜던스가 훨씬 더 좀 스트릭트한 컨디션이라는 거죠.
코릴레이션이 0이라 가지고 저게 서로 그 필요 충분 조건이 아니에요.
난 아니라고 했는데. 필요 충분해요?
왜냐면은
네.
만약에 이제 어떤 식유도 같은 걸 해서
네.
이제 만약에 그러니까
네.
X랑 X1이랑 X2가 이제 인디펜던트인지 아닌지는 모르는 상황에서 이제 이게 뭐 이게 나왔으면은
네.
이거면은 결국에는 이 뒤에 붙는 게 0이라는 소리인데
네.
근데 이제
그렇죠.
이걸 모르는 상태에서 이제
그러니까 인디펜던트하다는 조건이
이게
없어도
되면은 이게 된다라고 인디펜던트라고 할 수 없는 거죠.
그렇죠. 인디펜던트는 훨씬 더 스트릭트한 컨디션인 거예요. 그러니까 코베리언스는 이제 0이 될 수 있어요. 어떤 경우에. 그렇지만 코베리언스가 0이라고 이게 인디펜던트 하냐. 즉 이게 마지널과 y축의 어떤 값에서 잘라도 다 그게 디스트리뷰션이 완전히 다 동일하게 나와야 그게 이제 그 인디펜던스의 정의니까 훨씬 더
그럼 만약에 이 식을 유도를 해냈을 때 코베리언스가 0이네? 라고 하더라도 이걸 인디펜던트라고는 절대 말을 못하는 거죠. 저 지금까지 표충분 조건을 알고 있어가지고 그냥 문제에서 인디펜던트 주어지면 코베리언스 0 이거는 당연히 되는 거지만 거꾸로 이제 이런
네.
사실을 모르고 있을 때 만약 이런 식의 유도가 됐다고 한다면
네.
이거는 인디펜던트라고 사실은 생각을 했었던 그게 있었거든요. 이거는 표충분 조건.
네. 아마 내가 이야기한 게 맞을 것 같아요. 나도 이제 쪽에 지식이 많지는 않아서 한번 확인해 보세요. 또 네.
근데
네.
그러니까 네트워크에서 많이 쓰이고
쓰이기는 많이 쓰이죠.
근데 사실 학부 과정에서 쓰는 거는 거의 문제 푸는 정도밖에 없어가지고
그렇죠. 제대로 하면 굉장히 깊은 또 분야고 오랫동안 연구되었던 분야고. 네.